Introduction to Diffie-Hellman in IPSec. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are exploring one of the most elegant and crucial algorithms in cryptography, Diffie-Hellman key exchange, and its vital role in IPSec's IKEv1 and IKEv2 protocols. If you have ever wondered how two devices can agree on a secret encryption key over an insecure network without ever transmitting that key, this presentation will reveal the mathematical magic behind it. Diffie-Hellman, invented in 1976 by Whitfield Diffie and Martin Hellman, was a revolutionary breakthrough. It solved a fundamental problem in cryptography. How do you establish a shared secret between two parties who have never met and are communicating over an insecure channel? This algorithm is the foundation of secure key exchange in IPSec. In the context of IPSec, Diffie-Hellman serves a critical purpose. During IKE negotiations, it allows VPN peers to generate identical encryption keys without transmitting those keys over the network. Even if an attacker captures every packet of the IKE exchange, they cannot determine the shared secret. This property, combined with authentication, provides the security foundation for all IPSec communications. Throughout this presentation, I'll demystify the mathematics behind Diffie-Hellman, show you exactly how it's implemented in both IKE version 1 and IKE version 2, discuss the different DH groups and their security implications, and provide practical guidance on choosing the right groups for your deployments. We'll also explore modern threats and the evolution toward post-quantum cryptography. The mathematical foundation of Diffie-Hellman. Let me walk you through the mathematics of Diffie-Hellman in a way that makes intuitive sense. Do not worry if you are not a math expert. I will use analogies and clear examples to make this accessible. At its core, Diffie-Hellman relies on the properties of modular arithmetic and the difficulty of the discrete logarithm problem. Think of it like mixing paint colors. If I give you yellow and blue paint, you can easily mix them to get green. But if I give you green paint, it's virtually impossible to separate it back into the exact yellow and blue I started with. Diffie-Hellman works on a similar principle but with numbers. The algorithm uses a large prime number P and a generator G. These are public values that both parties agree on. Each party then generates a private random number. Alice chooses A, and Bob chooses B. These private values are never shared. Alice computes G to the power of a modulo P and sends this to Bob. Bob computes G to the power of B modulo P and sends this to Alice. Now comes the magic. Alice takes Bob's value and raises it to her private exponent, G to the power of B, all to the power of A. Modulo page Bob does the same with Alice's value, G to the power of A, all to the power of B. Modulo page due to the properties of exponents. Both calculations yield the same result, G to the power of AB, modulo P. This is their shared secret. The security comes from the discrete logarithm problem. Even if an attacker intercepts G to the power of a mod P and G to the power of B mod P, determining A or B from these values is computationally infeasible for large enough numbers. With a 2048-bit prime, an attacker would need more computational power than exists on Earth and more time than the age of the universe to break it through brute force. In IPSec, this shared secret is not used directly as an encryption key. Instead, it is fed into a key derivation function along with other values, for example, nonces exchanged during IKE, to generate the actual encryption keys, authentication keys, and other cryptographic material needed for the secure connection. Diffie-Hellman groups explained. Diffie-Hellman groups are predefined sets of parameters, the prime P and generator G, that have been standardized for use in cryptographic protocols. Think of them as different sizes of locks. Some are stronger than others, but stronger locks require more effort to use. The groups are numbered, and each number represents a specific set of parameters. Groups 1 through 5 are based on traditional modular exponentiation, MODP, with different prime sizes. For example, Group 1 uses a 768-bit prime, Group 2 uses 1024 bits, Group 5 uses 1536 bits, and Group 14 uses 2048 bits. The larger the prime, the more secure the exchange, but also the more computational power required. Starting with Group 19, we see elliptic curve groups. These provide equivalent security to much larger MODP groups but with smaller key sizes and faster computation. Group 19 uses a 256-bit elliptic curve that provides security equivalent to a 3072-bit MODP group. This efficiency makes elliptic curves particularly attractive for modern deployments. Choosing the right group involves balancing security, performance, and compatibility. Groups 1, 2, and 5 are now considered weak and should never be used in production. The current minimum recommendation is Group 14, 2048-bit MODP, for traditional DH, or Group 19, 256-bit ECP, for elliptic curves. For long-term security, consider Group 15, 3072-bit MODP, or Group 20, 384-bit ECP. One critical point. Both IKE peers must support the same groups. During negotiation, they'll agree on the strongest group that both support. This is why it's important to configure multiple groups in order of preference. Your VPN device will propose its preferred groups, and the responder will select the first one it also supports. Diffie-Hellman in IKE version 1 architecture. In IKE v1, Diffie-Hellman plays a crucial but complex role because of the protocol's multi-phase architecture. Let me explain exactly when and how DH is used in IKE v1's various modes. IKE version 1 phase 1 is where the initial Diffie-Hellman exchange occurs. In main mode, which uses 6 messages, the DH exchange happens in messages 3 and 4. The initiator sends its DH public value, KE payload, in message 3, and the responder sends its DH public value in message 4. This exchange is protected by the agreed-upon encryption algorithm but happens before authentication, which is a subtle but important detail. Aggressive mode condenses this into just 3 messages, with the DH values exchanged in the first 2 messages. While faster, this mode is less secure because identity information is exchanged before encryption is established. This is why main mode is preferred for site-to-site VPNs where connection speed is less critical than security. Phase 2, quick mode, is where things get interesting. You can optionally perform another DH exchange here for perfect forward secrecy. PFS without PFS. The Phase 2 keys are derived from the Phase 1 DH secret. With PFS enabled, a new DH exchange occurs in quick mode, ensuring that Phase 2 keys are independent of Phase 1. This means that even if an attacker somehow compromises the Phase 1 keys later, they can't decrypt previously captured Phase 2 traffic. One quirk of IKE v1 is that Phase 1 and Phase 2 can use different DH groups. You might use Group 14 for Phase 1 but Group 19 for Phase 2 PFS. This flexibility can be useful, but it also adds complexity to configuration and troubleshooting. In practice, I recommend using the same strong group for both phases unless you have specific requirements. Diffie-Hellman in IKE v2 architecture. IKE v2 significantly streamlines how Diffie-Hellman is used compared to IKE v1, making it both more efficient and easier to understand. Let me explain the elegant way IKE v2 handles DH exchanges. In IKE version 2, the initial Diffie-Hellman exchange occurs directly within the first 2 messages of the IKESA init exchange. The initiator includes its DH public value in the initial message, along with its supported cryptographic algorithms and a nonce. The responder immediately computes the DH shared secret and includes its own DH public value in the response. By the end of message 2, Both parties have computed the shared secret and derived all the keys they need. This is a significant improvement over IKEv1's approach. The DH exchange happens earlier, allowing encryption to start sooner. The entire IKESA establishment takes just 4 messages total, compared to 9 messages in IKEv1 main mode plus quick mode. This efficiency really matters for mobile users on high-latency connections. For child SA creation, equivalent to IKEv1's Phase 2, IKEv2 also handles PFS more elegantly. If you want PFS, you simply include DH values in the Create Child SA exchange. If not, you omit them. The protocol handles both cases seamlessly. There is no separate mode or complex configuration. PFS is just an optional parameter in the SA creation. Another improvement is DH group negotiation. If the responder doesn't like the initiator's proposed DH group, it can request a different one using an invalid KE payload notification. The initiator then retries with the requested group. This prevents the connection failure you might see in IK version 1 with mismatched DH groups. Instead, there's automatic negotiation to find a mutually supported group. Perfect forward secrecy PFS implementation. Perfect forward secrecy is one of those cryptographic concepts that sounds complex but is actually quite intuitive once you understand it. Let me explain why PFS is critical for security and how diffie-hellman enables it in IPSec. Without PFS, all your IPSec security associations derive their keys from the initial IKE key material. Think of it like a master key that opens many locks. If an attacker somehow obtains this master key, perhaps by compromising a device later, they could decrypt all traffic that was encrypted with keys derived from it. This includes traffic they might have captured and stored months or years ago. PFS breaks this relationship by performing a new diffie-hellman exchange for each child SA, or Phase 2 SA in IKE version 1. Each SA gets its own unique key material that is mathematically independent of all other keys. Even if an attacker compromises one key, they cannot use it to decrypt traffic from other SAs. It is like each door having its own unique lock with no master key. Implementing PFS does have a performance cost. Each DH exchange requires computational resources, generating random numbers, performing modular exponentiation, and deriving keys. For a site-to-site VPN creating 1 SA per hour, this overhead is negligible. But for a busy VPN concentrator handling hundreds of mobile users creating multiple SAs, the CPU impact can be significant. This is where choosing the right DH group becomes crucial. Elliptic curve groups like Group 19 provide strong security with much less computational overhead than traditional groups. In my deployments, I have seen Group 19 perform 3 to 5 times faster than Group 14 while providing better security. For high-volume scenarios, this performance difference enables PFS without overwhelming your hardware. My recommendation is simple. Always enable PFS for production deployments. The security benefits far outweigh the performance costs, especially with modern hardware and elliptic curve groups. The only exception might be IoT devices with extremely limited processing power, where the DH calculations could cause unacceptable delays. DH group selection and security considerations. Choosing the right diffie-hellman group is one of the most important security decisions you will make in your IPSec deployment. Let me guide you through the current landscape and help you make informed choices. First, let's talk about deprecated groups. Groups 1, which is 768-bit, and 2, which is 1024-bit, are cryptographically broken and must never be used. Group 5, which is 1536-bit, is on the edge. While not yet practically broken, it is below current security recommendations. If you are still using these groups, migration should be your top priority. I have seen production networks still using Group 2 because it has always worked. This is a ticking time bomb for security. For current deployments, Group 14, 2048-bit MODP, is the absolute minimum for traditional Diffie-Hellman. It provides approximately 112 bits of security, which is adequate for data that needs protection for the next 10 to 15 years. Group 15, 3072-bit, provides 128 bits of security, matching the strength of AES 128, while Group 16, 4096-bit, provides even more margin. Elliptic curve groups are where things get interesting. Group 19, 256-bit ECP, provides 128 bits of security, equivalent to Group 15 but with much better performance. Group 20, 384-bit ECP, steps up to 192 bits of security, matching AES 192. Group 21 uses a 521-bit curve. Yes, 521, not 512, providing 256-bit security to match AES 256. When selecting groups, consider your threat model and data sensitivity. For most corporate VPNs, Group 14 or Group 19 provides adequate security. For government or financial applications handling sensitive data, Group 20 or Group 15 might be required. Also consider your hardware capabilities. Older devices might not support elliptic curves or might perform them slowly without hardware acceleration. Always configure multiple groups in preference order. This provides fallback options and improves interoperability. For example, a typical configuration might list Group 19, Group 20, Group 14, Group 15. This prefers efficient elliptic curves but falls back to traditional groups for compatibility. Computational performance and optimization. The computational demands of Diffie-Hellman can significantly impact your VPN performance, especially at scale. Let me share insights from optimizing DH performance across various platforms and scenarios. Traditional MODP groups require modular exponentiation with very large numbers. For Group 14, 2048-bit, each DH calculation involves raising a number to a power modulo at 2048-bit prime. On a modern Intel CPU without optimization, this takes about 5 to 10 milliseconds. That might not sound like much, but when you're handling hundreds of tunnels, it adds up quickly. Elliptic curve groups change the performance equation dramatically. Group 19 calculations typically complete in 1 to 2 milliseconds on the same hardware. This represents a 5 times improvement. The math behind elliptic curves is different. It uses point multiplication instead of exponentiation, and it is inherently more efficient for the same security level. This is why I strongly recommend ECP groups for high throughput scenarios. Hardware acceleration makes a huge difference. Modern CPUs include instructions for accelerating both traditional DH and elliptic curve operations. Intel's ADX instructions accelerate large integer arithmetic, while specific EC instructions help with curve operations. Ensure your operating system and VPN software can utilize these features. On Linux, check /proc/CPU info for flags like ADX and AVX2. For truly high-scale deployments, consider dedicated crypto accelerators. Cards from vendors like Cavium or Intel QAT can offload DH calculations entirely, handling thousands of operations per second. I've seen a single accelerator card handle DH calculations for 10,000 plus concurrent tunnels without breaking a sweat. The investment is significant but can be justified for large VPN concentrators. Don't forget about software optimization. Pre-computing certain values, using optimized libraries like Open Secure Sockets Layer or Boring Secure Sockets Layer, and proper multi-threading can dramatically improve performance. In Strong Swan, for example, enabling multiple threads for crypto operations can linearly scale performance with CPU cores for DH calculations. Common implementation challenges. Over the years, I've encountered numerous Diffie-Hellman related issues in IPSec deployments. Let me share the most common problems and their solutions to help you avoid these pitfalls. The most frequent issue is DH group mismatch. The initiator proposes group 14, but the responder only supports group 5. In IKEV1, this often results in a cryptic no proposal chosen error. The logs might not explicitly mention DH groups, making troubleshooting frustrating. Always check that both peers have at least one DH group in common. In IKEV2, the invalid KE payload mechanism helps, but you still need compatible groups configured. Another common problem is PFS misconfiguration. One peer expects PFS DH in phase 2/child essay creation, while the other doesn't. This manifests as phase 1 succeeding but phase 2 failing. The solution is ensuring PFS settings match on both sides. In multi-vendor environments, terminology differs. Cisco might call it PFS Group 14 while Juniper refers to DH Group 14 for the same thing. Performance degradation under load often traces back to DH calculations. I have seen VPN concentrators CPU bound during tunnel establishment storms, for example, when hundreds of remote users reconnect after an outage. The symptoms include high CPU usage, slow tunnel establishment, and even timeouts. Solutions include using faster ECP groups, enabling hardware acceleration, or implementing connection rate limiting. Weak group vulnerabilities represent a serious security issue. Many organizations still have Group 2 enabled for compatibility with old devices. Attackers can force downgrade attacks, negotiating the weakest common group. Regular security audits should check for weak groups. Use tools like IPSec to verify what groups your VPN endpoints accept. Debugging tip: most VPN implementations can log DH calculations. In Strong Swan, enable debug level 2 for IKE. You will see messages like calculated shared secret with timing information. This helps identify if DH calculations are your bottleneck. For packet level analysis, Wireshark can decode IKE and show you exactly which DH groups are being proposed and accepted. DH security vulnerabilities and mitigations. While Diffie-Hellman is mathematically sound, several vulnerabilities have been discovered in how it's implemented and used. Understanding these threats is crucial for securing your IPSec deployments. The logjam attack, disclosed in 2015, showed that many implementations used weak or common DH parameters. The attack exploited 512-bit export-grade DH, Group 1, that could be broken in real time. More concerning, the researchers suggested that nation-states could break 1024-bit DH, Group 2, by pre-computing values for commonly used primes. This is why Groups 1, 2, and 5 are now considered insecure. Small subgroup attacks target implementations that do not properly validate DH public values. An attacker sends a carefully crafted public value that results in a weak shared secret. Modern implementations include subgroup validation, but older devices might be vulnerable. Always keep your VPN software updated to include these security checks. Timing attacks can potentially leak information about private DH values due to variations in computation time. While this is theoretical for most deployments, high-security environments should use implementations with constant time DH operations. Most modern crypto libraries include these protections, but for critical deployments, you should verify with your vendor. Quantum computers pose a future threat to all current DH groups. Shor's algorithm can efficiently solve the discrete logarithm problem that DH relies on. While large-scale quantum computers don't exist yet, planning for post-quantum cryptography is important for long-term security. The IETF is working on quantum-resistant key exchange methods that will eventually replace or supplement current DH groups. Mitigation strategies include using only strong DH groups, 14+ for MODP, 19+ for ECP, enabling PFS to limit breach impact, regularly updating VPN software, monitoring for downgrade attacks, and planning for post-quantum migration. Document your current DH usage to facilitate future upgrades when quantum-resistant algorithms become standardized. Diffie-Hellman in multi-vendor environments. One of the biggest challenges with diffie-Hellman in IPSec is ensuring interoperability across different vendors. Each vendor seems to have their own terminology and default settings. Let me help you navigate this maze. Cisco ASA and iOS use straightforward DH group numbers in their configuration. You will see Group 14 or Group 19 in the crypto maps. However, older iOS versions might not support elliptic curve groups, limiting you to traditional MODP groups. Cisco's default often includes weak groups for backward compatibility, so always explicitly configure your allowed groups. Juniper SRX refers to DH groups differently in various contexts. For IKE proposals, you will use DH Group 14 or DH Group 19. For PFS, it is Group 14 or Group 19. This inconsistency can be confusing. Juniper also supports custom DH groups, which can cause interoperability issues if not carefully managed. Fortinet FortiGate uses yet another naming scheme. They refer to DH groups as DH Group 14, DH Group 19, etc. FortiOS also has aggressive defaults that might propose many DH groups, including weak ones. I always recommend creating custom Phase 1 and Phase 2 selectors with only strong groups. Open source implementations like StrongSwan and OpenSwan use the standard names, but might support different subsets of groups. StrongSwan has excellent support for all modern groups, including the latest ECP curves. However, its defaults can be too permissive, accepting weak groups if offered. For successful multi-vendor deployments, I recommend creating a standardization document listing the exact DH groups to use, how each vendor refers to them, and configuration examples. Test every vendor combination in your lab before production deployment. Use packet captures to verify which groups are actually being negotiated. Do not trust the configuration alone. Advanced DH features in modern implementations. Modern IPSec implementations have introduced several advanced features around diffie-Hellman that can enhance security and performance. Let me highlight the most important ones you should know about. DH group guessing is an IKEv2 optimization where the initiator can include multiple KE payloads with different DH groups in the first message. This prevents the round trip needed if the responder prefers a different group. While this speeds up connection establishment, it is most useful in environments with diverse DH group requirements. Hybrid post-quantum key exchange is beginning to appear in bleeding-edge implementations. These combine traditional DH with quantum-resistant algorithms like New Hope or Sight. The idea is that even if one algorithm is broken, the other still provides security. Google has experimented with this in Chrome, and we will likely see it in IPSec implementations soon. DH key reuse is a performance optimization where the same DH private value is used for multiple exchanges. While this can significantly reduce CPU load, it has security implications. If the private value is compromised, multiple connections are affected. Some implementations allow configuring DH key lifetime to balance performance with security. Hardware Security Module (HSM) integration for DH operations is becoming more common. HSMs can generate and store DH private keys, ensuring they never exist in system memory where they could be compromised. For high-security deployments, HSM-backed DH provides an extra layer of protection against key extraction attacks. Adaptive DH group selection is an emerging feature where VPN gateways can automatically adjust their DH group preferences based on CPU load and security requirements. During high load, the system might prefer faster groups, like Group 19, while switching to stronger groups, like Group 20, during quieter periods. This dynamic adaptation helps balance security and performance automatically. Troubleshooting DH-related issues. When IPSec connections fail, diffie-hellman issues are often the culprit. Let me share my systematic approach to troubleshooting DH-related problems, developed over years of midnight debugging sessions. Start with the basics. Enable detailed IKE debugging. Every platform has different commands. For example, debug crypto ISAKMP on Cisco, debug IKE-all on Juniper, and Karen.log equals IKE2 on StrongSwan. Look for messages about DH group negotiation, KE payload processing, and shared secret calculation. These logs often reveal the exact mismatch. Packet captures are invaluable for DH troubleshooting. In Wireshark, filter for ISAKMP or IKE-v2 and examine the SA proposals. The KE payload shows the DH group being used. The payload length indicates the group: 768 bytes for group 14, 256 bytes for group 19, etc. Compare what each peer sends to identify mismatches. Here are common error messages and their meanings. No proposal chosen often indicates DH group mismatch in IKE-v1. Invalid KE payload in IKE-v2 explicitly means the responder wants a different DH group. Peer didn't give DH group suggests PFS misconfiguration. DH group X not supported is self-explanatory, but check if it's a licensing or software version issue. Performance-related DH issues manifest as slow tunnel establishment or high CPU during IKE negotiation. Use system monitoring to check if CPU spikes correlate with IKE events. The command show crypto IPSec SA detail, or equivalent, often includes DH computation times. If DH calculations take over 100 milliseconds, you have a performance problem. For intermittent issues, check if DH group negotiation succeeds sometimes but fails other times. This often indicates load-related problems or race conditions. Some implementations have bugs where concurrent DH calculations interfere with each other. Rate-limiting IKE connections or upgrading software usually resolves these issues. DH configuration best practices. After years of deploying and troubleshooting IPSec, I have developed a set of best practices for diffie-hellman configuration. These guidelines will help you build secure, performant, and maintainable VPN deployments. First, standardize on a minimum set of strong DH groups across your organization. I recommend supporting groups 14, 19, and 20 as your standard set. Group 14 provides compatibility with older devices, while groups 19 and 20 offer better performance and security. Document this standard and enforce it through configuration management. Always configure DH groups in order of preference, strongest first. For example, an Internet Key Exchange, or IKE, string might be IK equals AES 256 SHA 384 ECP 384. AES 256 SHA 384 ECP 256. AES 256 SHA 384 MODP 2048 exclamation mark. This ensures you get the best security possible while maintaining compatibility. The exclamation mark in StrongSwan means strict mode, only these proposals, no defaults. Enable PFS for all production IPsec connections. The security benefits far outweigh the minimal performance impact on modern hardware. For high-throughput scenarios, use ECP groups for PFS to minimize CPU overhead. Configure PFS with the same or stronger group than your Phase 1/IKESA. Implement a regular review process for DH group usage. Every quarter, audit your VPN logs to see which DH groups are actually being negotiated. If you are still seeing Group 5 or lower, investigate immediately. Use this data to plan the deprecation of weak groups and migration to stronger ones. For new deployments, be assertive about DH requirements. Start with only groups 19 and 20 enabled. Add weaker groups only if absolutely necessary for specific interoperability requirements, and document why. It is much easier to relax security requirements later than to tighten them after deployment. Future of DH. Post-quantum considerations. The advent of quantum computing represents an existential threat to current Diffie-Hellman implementations. Let me explain what this means for your IPSec deployments and how to prepare for the post-quantum era. Quantum computers exploit quantum mechanical properties to solve certain mathematical problems exponentially faster than classical computers. Shor's algorithm, running on a sufficiently large quantum computer, can solve the discrete logarithm problem that DH security relies on. Current estimates suggest a quantum computer with a few thousand stable qubits could break even our strongest DH groups. The timeline is uncertain but concerning. While today's quantum computers are too small and unstable to threaten DH, progress is accelerating. IBM, Google, and others are rapidly scaling up their quantum systems. Conservative estimates put cryptographically relevant quantum computers 10 to 20 years away, but breakthroughs could shorten this timeline dramatically. The harvest now, decrypt later threat is immediate. Adversaries can capture and store encrypted traffic today, then decrypt it once quantum computers become available. For data that needs long-term confidentiality, medical records, trade secrets, government communications, this is a serious concern. Even with PFS, the initial IKE exchange could be broken retroactively. Post-quantum key exchange algorithms are being developed and standardized. NIST is running a competition to select quantum-resistant algorithms. Leading candidates include lattice-based systems like New Hope and Crystal's Kyber. These algorithms resist both classical and quantum attacks, but require larger key sizes and more computation than current DH. Hybrid approaches offer a transition path. By combining classical DH with post-quantum algorithms, we get security against both current and future threats. Even if the post-quantum algorithm has undiscovered weaknesses, the classical DH still provides protection. IPSec implementations are beginning to experiment with these hybrid modes, and we will likely see standardization in the next few years. DH in cloud and SDN environments. Cloud and software-defined networking environments present unique challenges and opportunities for Diffie-Hellman in IPSec. Let me share insights from deploying DH-based VPNs across major cloud platforms and SDN architectures. Cloud providers often have specific DH group requirements and limitations. AWS VPN connections default to groups 2, 14, 15, 16, 17, 18, 19, 20, and 21 for Phase 1, but only groups 2, 5, 14, 15, 16, 17, 18, 19, 20, and 21 for Phase 2. You will notice that Group 5 appears in Phase 2 but not Phase 1. These inconsistencies can cause confusion. Always explicitly configure your customer gateway to use only strong groups. Azure VPN Gateway supports a different set of groups and allows custom IPsec policies. You can specify exact DH groups for both IKE and IPsec SAs. Azure's route-based VPNs perform better with ECP groups due to the cloud infrastructure's optimization for elliptic curve operations. Policy-based VPNs might have more limited DH group support depending on the gateway SKU. In SDN environments, the separation of control and data planes affects DH implementation. The SDN controller might negotiate IKE/IPsec parameters centrally, then push the derived keys to data plane devices. This architecture can centralize DH computations on powerful controller hardware while distributing the simpler encryption/decryption tasks. It is an elegant solution for scaling IPsec in large networks. Container and microservice architectures present new challenges. Each container might need its own IPsec tunnel, potentially requiring thousands of DH calculations. Solutions include session resumption to avoid repeated DH exchanges, hierarchical key distribution where containers inherit keys from their host, or using alternative protocols like WireGuard that have different key exchange models. Automation is crucial in cloud environments. Use infrastructure as code to manage DH group configurations consistently across hundreds of VPN connections. Tools like Terraform can ensure your DH group policies are applied uniformly. Include DH group verification in your CI/CD pipelines to catch configuration drift before it causes production issues. Real-world DH deployment scenarios. Let's examine real-world scenarios where diffie-hellman configuration made the difference between success and failure. These cases illustrate important lessons for your own deployments. Case 1. A financial services company was experiencing intermittent VPN failures during trading hours. Investigation revealed their VPN concentrators were becoming CPU-bound while performing Group 16, 4096-bit, DH calculations. Each calculation took 50 to 100 milliseconds, and during market open, hundreds of traders connected simultaneously. The solution was to migrate to Group 20, 384-bit ECP, which reduced calculation time to under 5 milliseconds, while still maintaining equivalent security. The elliptic curve operations were also hardware accelerated on their platform. Case 2. A healthcare network merger required connecting two organizations with different security standards. Organization A mandated Group 15 minimum, while Organization B's legacy medical devices only supported Group 2. Solution. We implemented a DMZ with VPN proxies that performed protocol translation. External connections used Group 19, while legacy devices connected to the proxy using Group 14, the strongest they supported, over isolated, monitored segments. This maintained security while enabling critical medical device connectivity. A global manufacturer discovered their IoT devices were failing to establish VPNs from certain countries. The issue was traced to deep packet inspection firewalls blocking large UDP packets. The Group 15 DH exchange exceeded MTU limits when combined with IKE headers and NAT-T overhead. The solution was to switch to Group 19, which reduced packet sizes below the threshold while providing better security. We also implemented IKE fragmentation for locations that needed larger groups. Advanced DH features in modern implementations. Modern IPSec implementations have introduced several advanced features around diffie-hellman that can enhance security and performance. Let me highlight the most important ones you should know about. DH group guessing is an IKE-v2 optimization where the initiator can include multiple KE payloads with different DH groups in the first message. This prevents the round trip needed if the responder prefers a different group. While this speeds up connection establishment, it is most useful in environments with diverse DH group requirements. Hybrid post-quantum key exchange is beginning to appear in bleeding-edge implementations. These combine traditional DH with quantum-resistant algorithms like New Hope or Sight. The idea is that even if one algorithm is broken, the other still provides security. Google has experimented with this in Chrome, and we will likely see it in IPSec implementations soon. DH key reuse is a performance optimization where the same DH private value is used for multiple exchanges. While this can significantly reduce CPU load, it has security implications. If the private value is compromised, multiple connections are affected. Some implementations allow configuring DH key lifetime to balance performance with security. Hardware Security Module (HSM) integration for DH operations is becoming more common. HSMs can generate and store DH private keys, ensuring they never exist in system memory where they could be compromised. For high-security deployments, HSM-backed DH provides an extra layer of protection against key extraction attacks. Troubleshooting DH-related issues. When IPSec connections fail, diffie-hellman issues are often the culprit. Let me share my systematic approach to troubleshooting DH-related problems, developed over years of midnight debugging sessions. Start with the basics. Enable detailed IKE debugging. Every platform has different commands. For example, debug crypto ISAKMP on Cisco, debug IKE-all on Juniper, and Karen.log equals IKE2 on StrongSwan. Look for messages about DH group negotiation, KE payload processing, and shared secret calculation. These logs often reveal the exact mismatch. Packet captures are invaluable for DH troubleshooting. In Wireshark, filter for ISAKMP or IKE-v2 and examine the SA proposals. The KE payload shows the DH group being used. The payload length indicates the group. 768 bytes for group 14, 256 bytes for group 19, etc. Compare what each peer sends to identify mismatches. Here are common error messages and their meanings. No proposal chosen often indicates DH group mismatch in IKEv1. Invalid KE payload in IKEv2 explicitly means the responder wants a different DH group. Peer didn't give DH group suggests PFS misconfiguration. DH group X not supported is self-explanatory, but check if it's a licensing or software version issue. DH configuration best practices. After years of deploying and troubleshooting IPSec, I have developed a set of best practices for diffie-hellman configuration. These guidelines will help you build secure, performant, and maintainable VPN deployments. First, standardize on a minimum set of strong DH groups across your organization. I recommend supporting groups 14, 19, and 20 as your standard set. Group 14 provides compatibility with older devices, while groups 19 and 20 offer better performance and security. Document this standard and enforce it through configuration management. Always configure DH groups in order of preference, strongest first. For example, an Internet Key Exchange, or IKE, string might be IK equals AES 256 SHA 384 ECP 384, AES 256 SHA 384 ECP 256, AES 256 SHA 384 MODP 2048 exclamation mark. This ensures you get the best security possible while maintaining compatibility. The exclamation mark in StrongSwan means strict mode, only these proposals, no defaults. Enable PFS for all production IPsec connections. The security benefits far outweigh the minimal performance impact on modern hardware. For high-throughput scenarios, use ECP groups for PFS to minimize CPU overhead. Configure PFS with the same or stronger group than your Phase 1/IKESA. Implement a regular review process for DH group usage. Every quarter, audit your VPN logs to see which DH groups are actually being negotiated. Future of DH. Post-quantum considerations. The advent of quantum computing represents an existential threat to current diffie-hellman implementations. Let me explain what this means for your IPsec deployments and how to prepare for the post-quantum era. Quantum DH in cloud and SDN environments. Cloud and software-defined networking environments present unique challenges and opportunities. Real-world DH deployment, performance benchmark, security hardening, and conclusion and future outlook. As we conclude our deep dive into diffie-hellman in IPsec, let me summarize the key insights and provide guidance for future-proofing your deployments. Diffie-hellman remains the cornerstone of IPsec key exchange, enabling secure communication over untrusted networks. Its elegant mathematics, allowing two parties to agree on a shared secret without transmitting it, continues to protect millions of VPN connections daily. Understanding DH deeply is not just academic, it directly impacts the security and performance of your network infrastructure. The evolution from IKEv1 to IKEv2 has streamlined how DH is used, reducing complexity while improving security. IKEv2's efficient four-message exchange and superior error handling make it the clear choice for new deployments. If you are still running IKEv1, migration should be a priority. The operational benefits alone justify the effort. Current best practices are clear. Use group 14, 2048-bit, as your minimum for traditional DH. Prefer groups 19 or 20 for elliptic curves. Always enable PFS, and regularly audit for weak groups. The performance advantages of ECP groups make them ideal for most deployments. Hardware acceleration, whether CPU instructions or dedicated cards, can eliminate DH as a performance bottleneck. Looking ahead, the post-quantum threat looms large. While quantum computers capable of breaking current DH are likely years away, the harvest now, decrypt later threat means we need to act soon. Hybrid classical/post-quantum approaches offer a pragmatic transition path. Stay informed about NIST's post-quantum standardization efforts and be prepared to update your infrastructure. Your action items. Audit your current DH group usage across all VPN endpoints. Eliminate groups 1, 2, and 5 immediately. Standardize on groups 14, 19, and 20. Enable PFS everywhere. Document your cryptographic standards. Plan for post-quantum migration. Most importantly, make cryptographic agility a design principle. Your infrastructure should support algorithm updates without architecture changes. Thank you for your attendance. Please consider subscribing to the channel.